All right, class, let's take a look at example 2. So in this particular case, we want to figure out what the internal forces are in our column here. So let's swap this here. So our goal is to find those internal forces at E. So I'm going to write that here. Find VE, ME, and normal force at E. Now I'm going to switch this a little bit here. And let's just go here and look at this. So now our goal in this case is to find those internal forces. The first thing I always want to do is start with my reactions. Now in this particular case, I'm going to look at the whole structure to help me find the reaction. So what I'm going to do is I'm basically going to cut this cable here. So I'm going to call this a tension force here. Let me get a marker that works. Call this a tension force here. I've got a pin at A. Let's call that AY and AX. And I'm drawing the AY vertically because I think it's going to counteract this 150. And I'm trying to draw AX going to the right because I know this tension force is going to create some tension, and those two are going to work together to keep this thing stable. All right. So first, like before, we're going to find our reactions. So find AY and AX. I'm going to put my focus there, and I'm going to tell you why in just a second. But if I'm looking at this, I can assume this tension X here, or I could move this tension all the way up here to be Y, right? Using that property of transmissibility, I'm going to move that using the trans property, I'm going to move that tension here. Why is that? If I do a moment about B, this is a clever way to do this because, hey, I've got AY passes, its line of action goes right through B. The other advantage is that tension also, its line of action goes through B. So if I take a moment about B, this is going to directly tell me what A of X is. Because A of X is my only unknown. So now I know A of X. If I know A of X, I can use the sum of forces in the X direction. I can use the sum of forces in the X direction to figure out what my tension is. And then I can use my sum of forces in the Y direction. That's going to tell me what A of Y is. Right? I've now conveniently wrapped this whole problem up. I know what AX and AY are. Now you're going, okay, Albert, you now have your reactions. I still don't see how we're going to find what's going on at E, right? Our goal is to find out what our internal forces are at E. So the next step of this is the crucial part, is to draw that free body diagram. Draw a free body diagram. And now I want to be clever here. I could look at the top part. It was totally viable. But if I look at the top part, it's a lot more complex. I could look at just the bottom part. I want to look at that cut going this way. So I'm going to draw that here. I'm going to draw that. I'm going to look at the bottom part of that cut. I'm going to look at section AE. Or I could say this cut, I'll call it cut AA. Taking that cut, I'm going to expose my internal forces there at E. I'm also going to have my reactions at AY and AX, but I already know what these are. I can then figure out what E is going to be, right? Now in this particular case, because I've cut it this way, my normal is going to be this way. My shear, well, we still have to think about this. What creates a clockwise rotation? Clockwise rotation would be this way, so this would be positive shear. And positive moment, this is a little more complicated when we turn it sideways. I'm just going to draw a positive moment this way. Now I've got those things there. And because I already know what AY and AX are, I've just got those three unknowns. I can use my equations of equilibrium in my third step my equations of equilibrium to figure out what those are, right? From sum of forces in the y, I'm going to find that AY, that our normal force at E is negative AY. From sum of forces in the X is 0. I'm going to find that VE is negative AX. And then I could take a moment about E to figure out what moment E is going to be. And I'll do that in just a second. So there are all of our steps. Before I even bust out my calculator, I know how to solve this. Calculator handy. Let's figure out what these are going to be. So taking a moment about B is going to give us what AX. So let's start there. To find our moment about B, I know that I only have AX, and I've got this vertical force of 100 pounds. That's the weight of our bucket. So let's do that. If we take that distance, I've got 150 pounds times its lever arm. In this case, that's 4 feet. That creates a negative moment. And then I've got AX. Now AX, as I've drawn it, creates a positive moment. Its lever arm is the total height of our structure here. That is going to be 6 feet. Fix that here, 6 feet, which means A of X is going to be 600 divided by 6. This is going to be 100 pounds. And I've drawn this in the correct orientation, going to the right. All right. So now I have A of X. From sum of forces in the X direction, I'm going to get T. And I am missing a crucial dimension here. This is the one reason to make your diagrams as neat as possible. I need to get that horizontal distance there. All right, I don't need a horizontal distance. They gave me 30 degrees here. So that 30 degrees is going to help tell us what part of this is acting in the X direction. So if we think about this, I have tension, and this is going to be sine of 30 degrees based off of this vertical here. That's going to be 30 degrees. The nice thing about sine of 30 degrees, we know that's going to be 1/2. So it's negative T sine 30 plus A of X. A of X is acting in the positive direction. So that's 100 pounds here. Now, like I said, I'm not a conspiracy theorist, but I think they made the math easier for us on purpose. If this is 1/2, and you can plug it into your calculator and check, then I know that T is just going to look like 200 pounds. And that means it's acting in the direction we expected, which is the only direction it can act, right? Tension. You can't put a cable in compression. It's just going to, it's going to stop being taught and stop doing any structural work. All right, so now I know the tension. I can come over here and find out what AY is using sum of forces in the Y. In that case, I've got the negative 150 pounds of the bucket acting down. I've also got tension. That's also acting down, but not all of it. It's going to be 200 pounds. In this case, cosine of 30 degrees. And then I've also got AY. That's the only thing acting up to counteract these things, which means AY is going to be 150 pounds plus 200 cosine of 30 degrees. And if I plug that into my calculator, I got 150 plus 200 cosine of 30 degrees. Make sure your calculator's in degrees. I get a force of 323 pounds. All right, so now I know what those two values are. I know A of X and A of Y. Those are the two important ones. A of Y is 323. 100 pounds is A of X. So putting these two things together, knowing what those values are, I know our normal force is going to be negative 323 pounds. Our shear force is going to be negative 100 pounds. And our moment, we have to do a little bit more work for. To find our moment, we're going to take our moment about E. That's going to get rid of those two new quantities. AY is not going to create any moment. The only thing creating moment is A of X. So A of X, we said, was 100 pounds. So we got 100 pounds times this distance. I'm missing that crucial dimension here, so I'm going to come back over here. That's going to be 3 feet. 3 feet. So it's going to be 100 pounds times 3 feet plus our moment. Now let's think about A of X. A of X is acting, that's positive. Our ME is also positive as we've drawn it, which means our, well, it's got to be going the other way. We're going to get a negative value here. Our moment, internal moment at E is actually going to be negative 300 pound-feet. And keeping that all in mind, we know that that's going to be negative 300 pound-feet. Now we have our moment, we've got our shear, we've got our normal force. If we go back to our find, which we should always do at the end, we've got shear, we've got moment, and we've got normal force at E. And that's how you find the internal force in a column.